This video provides guidance for the safe operation of low-energy X-ray diffraction machines used by structural biologists. It is intended to supplement the formal instruction provided in each institution and each laboratory. This video is not a substitute for a safety training program. Dr. Stephen Harrison studies the structure of viruses and their receptors, including the CD4 protein used as a receptor by the AIDS virus. Determining the structure of viruses and proteins is the first step in understanding how they interact. The principal investigative technique of Steve and his colleagues at Harvard is X-ray diffraction. X-rays are a form of radiation that can cause cell destruction as well as genetic damage.
If you've worked with something that is a known hazard, there are two things. First, you have to respect what's hazardous about it. Second, it's terribly important not to be afraid of it if you know that there are appropriate safety measures you can take that will ensure that you're not going to be exposed to an undue hazard. So in the case of X-rays, which is what we're talking about today, then what's important is to understand, given the kind of X-ray generators and sources we use and the kind of X-ray beams and X-ray optics that we're dealing with, what the real hazards are and how to work safely around an X-ray beam.
Steve Harrison is a veteran in the now burgeoning field of structural biology, whose diffraction machine is an old unit requiring manual alignment of the beam. The beam energy is low. Its principal component is the characteristic radiation from copper at 8 keV. A radiation survey with the Geiger counter detects scatter, which results from the beam striking any obstruction, including air. In this case, the scatter from Steve's machine is relatively low because the finely focused beam has a diameter of less than 2 millimeters. The highest measured radiation at this point is 0.2 millirems per hour, which is not much greater than background. Past measurements with multiple finger and collar dosimeters during the alignment procedure have shown no reportable dosimeter response. A monitoring badge provides a record of any cumulative exposure. Of course, the most significant X-ray hazard is the beam itself. The dose rate in the direct beam is tens of thousands of rems per hour, which means almost any exposure can result in skin burns. Steve remains constantly aware of the on-off status of the X-ray beam. Whenever placing his hands close to its path, he repeatedly verifies that the shutter is closed. This discipline is never compromised, even though warning lights alert him when X-rays are being generated and when the shutter is open. Aligning the X-ray beam is best undertaken by a skilled worker. Doing it properly requires complete concentration. Newer X-ray machines are aligned by remote control, keeping the operator at a safe distance from the beam.
The most important thing, that even above all of the safety rules, is that a person has an understanding of the potential danger of the situations. And it should be a reasonable danger. It shouldn't be exaggerated. A lot of times people are terrified of radioactivity or X-rays to the point where they become unreasonable about it and therefore don't adopt a sensible and healthy attitude.
The experienced structural biologist understands the potential non-radiation hazards associated with X-ray diffraction. For example, the now popular technique of freezing crystals in liquid propane calls for some caution. The supply tank is stored and used in a fume hood. Yusuf Shamu uses a commercial tank with a heavy-duty cutoff valve. A control valve allows easy dispensing of the propane. propane will freeze at liquid nitrogen temperature, and crystals can thus be stored indefinitely and easily transported. But remember, frozen propane has a much higher heat capacity than liquid nitrogen. Contact with skin can result in serious burns. The cutoff valve should always be closed when the equipment is not in use. Routine operation of the X-ray diffraction machine presents few hazards. Still, it's important for users to be familiar with the safety requirements and proficient in its operation. At all times, Yusuf is alert to the on-off status of the beam. He wears cotton gloves under disposable gloves when handling the frozen vial. Yusuf knows that keeping his fingers any length of time in the liquid nitrogen stream could cause frostbite, and he's careful not to get melting propane droplets on his skin while positioning the sample. Yusuf has a keen sense of the beam. He has disciplined himself never to cross its path, even when the shutter is closed. Lead acrylic shields provide protection from scatter radiation. The synchrotron is the newest tool available to the structural biologist. Its X-ray beam intensity can be 100 to 1,000,000 times higher than that of a home diffraction machine. Since contact with the direct beam would cause immediate serious injury, safety is built in with permanent shielding and secure interlocks.
It's actually much more difficult to make a mistake at the synchrotron than it is at home. This is the consequence of having a truly dangerous beam compared to the dangerous but not as devastatingly dangerous an X-ray source as we have at home. For that reason, the facilities have necessarily made up procedures that are going to guard against that. You can't get close to the apparatus without first shutting down the beam. That's also an encumbrance. You can't do manipulations easily, and as a result, much of the facility is more automated than has been traditionally the case at home. With due caution, the practice of X-ray diffraction experimentation is not, in our view anyway, at all hazardous. I mean, not more so than a lot of other scientific activity, not more so than being a chemist working with a lot of potentially toxic compounds. Again, not a problem as long as you handle things appropriately.